First, we want to look at the additive property of definite integrals. So say we want to take the integral of some function over some interval a to b. So just look at this picture down here. So this picture represents the integral of f of x from a until b. So that's this entire area here underneath this curve from a to b. But now instead say, let's split this up. I want to first find the area from a to c. So that would be the integral from a to c of the function f. And then I also next want to find the area from c to b. So that would be the integral from c to b of the function f. So what this theorem says is that I can add those two areas together and it'll give me the total area from a to b. So what it tells us is we can break up the total area into two pieces or three pieces, or really as many pieces as we want to, as long as we're still covering the entire interval. And notice I start at a, so that's my starting point here. And then I go all the way until c. So that's my ending point for this first integral. Then for my second interval and my second integral, my starting point c now, and then I go all the way until b, so that will be my end point. So you can see that the first integral stops at c, and the second integral has to begin at c. We can't miss anything, so we have to, wherever we stop, we have to start the next one at that point. So the good thing about this property, this theorem, is it allows us to integrate continuous piecewise defined functions. Functions that are not defined the same over the entire interval we want to find the area of. So for this example, we want to find the area under the graph of f, and f is a piecewise defined function. And we want to find the area from -4 to 5. And so this is a graph of what the function f looks like. So you can see from -4 to 5, -4 to 5 is the entire area we want to find. But you can see on the graph from -4 until 3, the function kind of just looks like a rectangle. And then from 3 until 5, the function looks a little bit different. So we're going to have two pieces that we need to integrate. We have this piece right here, and then we have this piece. So we'll have to divide up our integral. First we'll have from -4 to 3. That's our first piece. And then our second piece will be from 3 to 5. So that's how we're going to divide up our integral, so that we can evaluate the integral of this piecewise defined function. And also, if you just look at the definition of the piecewise defined function, you can see that 3 is the cutoff point. 3 is the place where the function changes. So we know that 3 is going to be like our intermediate point. The ending point for the first integral and the starting point for the second integral. It's going to be our dividing point. So we know that what we want to find is the integral from -4 to 5 of our function f. And so we know we can break that integral up into these two different pieces. So the integral from -4 to 3, and then the integral from 3 to 5. We're not just doing this for the fun of it, we have to do it this way because the function is defined differently on these two different intervals. So if we wanted to take the integral from -4 to 5, so we just wanted to calculate this one directly, we wouldn't know if we wanted to use x squared or 9 because the function is defined differently on that interval. So we break it up into this, these two guys over here, because from -4 to 3, the function is just defined as 9. Because we know whenever x is less than 3, the function is just equal to 9. And then from 3 to 5, the function is just equal to x squared. Because we know whenever x is greater than or equal to 3, the function equals x squared. So that's why we have to break it up like that. So now I plug in the value of the function for each integral. And now I can simply just start evaluating each of these integrals. So if you want to, you can evaluate each integral separately and then plug in the answer you get, which may be a good idea. Or you can just calculate it all together. So maybe I'll just go ahead and pull each integral out and calculate it separately. So first let's look at the integral of 9 from -4 to 3. So first, just the antiderivative of 9 is just 9x. And we're evaluating this from -4 to 3. So now we can just plug in our limits. So we have 9 times 3 minus 9 times the second limit, which gives us 63. So we know the value of this first integral is 63. Okay, now let's find the value of the second integral. So first we need to find the antiderivative of x squared, which we know is just 1/3 times x cubed. And then we write this intermediate step where we keep in mind what our limits are. Now we can plug in the limits of integration, which will give us this. And just a point, you can leave the 1/3 on the outside if you want to. You can factor it out and just write this as 5 cubed minus 3 cubed. Either way is fine. So when we evaluate this, we'll get 98 over 3. So we know the value of the second integral is 98/3. So now we can plug in that value and also the value for the first one. So plugging in the values of the two integrals that we found, we have 63 plus 98 over 3. And when we add those together, we get 287 divided by 3. Which, if you want to write that as a mixed number, you can write it as 95 2/3. Or as a decimal approximation, you can write it as 95.66 repeating. So that's our answer for this problem. So that's the area under this curve. So whenever you have piecewise defined function, you have to break it up into pieces where on that piece the function is only defined in one way. You can't evaluate an integral where the function is defined in two different ways on that same integral.